Hello guys, welcome to my channel Learning Space, and today we will learn about heat transfer from extended surface called fins. So let's start. First topic is fins. A fin is a surface extension. So it is generally an extended surface of an object and it is used for increasing the heat transfer rate from an object. Suppose we have an rectangular object. This is our rectangular object. Now this is extended by a surface. This surface is called as fin. So this part is called fin. So we generally use this for increasing the rate of heat transfer. We all know about heat transfer rate through convection, which is given by this general formula. So here we can observe that heat transfer is directly proportional to area. Since H is constant and temperature difference is constant, so if we increase the rate of surface area, if we increase the surface area, then rate of heat transfer will increase. So that's why we make fins on the surface of object. There are many applications of fins. First application is radiators of automobiles. So these are fin to release the heat. Second application is in air-cooled engine cylinder heads. So you can observe head of cylinders fin so that heat produced inside the cylinder in power stroke can be released. Third application is cooling coils and condenser coils in refrigerators and air conditioners. So you have seen at the back of your refrigerators, they are condenser coils. So these are also fin. Fourth application is in economizers for steam power plant, and fifth application is in electric motor bodies. So you have observed the motor having fin surface. So again it is used for releasing the heat produced inside so that the components can work properly. For proper design of fins, we should know the assumptions so that we can design different types of fins like rectangular fins, trapezoidal fins, or any type of fins which are required. First assumption is steady state heat condition. So heat should be steady. It should not be unsteady. So heat should be steady state, in steady state. When we talk about second assumption, then it says that there should not be internal heat generating element in the fin. So there should not be any internal heat generation in our surface. So suppose this is our surface, there should not be internal heat generation. No internal heat generation. Third assumption is uniform heat transfer coefficient over the entire surface of the fin. So suppose this is our fin. So there should not be any heat generating element which we talked in point 2. Now third point says that H should remain constant over the entire surface. Now it should not vary over different lengths of fin. Fourth assumption is material should be homogeneous and isotropic. So this fin material should be homogeneous and isotropic. It means that thermal conductivity of material should be constant in all direction, that is Kx equal to Ky, that is in all direction x, y and z. The value of thermal conductivity should be constant. Now fifth point says that negligible contact thermal resistance. Now if surface are in contact, then their thermal resistance develops. So here thermal contact resistance should be negligible and there should not be any radiation. So here radiation is neglected. So we are not talking about radiation. So there should not be any radiation. We call it negligible radiation. So these are the assumptions. So first we will discuss about heat flow through rectangular fins. So the figure shows a rectangular fin. This is our rectangular fin. Now we will define certain parameters like L. Now L here denotes the length. So I am denoting it by small l. So L is length of fin and length is generally perpendicular to surface from which heat is to be removed. Suppose we have to remove heat from this surface, then this length should be in perpendicular to the surface. Now B is our width. So this is our width of the fin, and it should be parallel to surface from which heat is to be removed. So here you can observe that heat is parallel to the surface, and y is thickness of the fin. So this is our thickness. So I am denoting this by y, and generally we have to use perimeter of this exposed surface. So we define perimeter with symbol P, and we can calculate it with general formula. And this green element shown here is our element which we have considered for deriving the equation. So I will only give you the boundary conditions and different parameters to derive the equation. And we have to calculate the cross-sectional area. So this is our ACS. I'm representing this with ACS. This is our area of cross section, which can be calculated by formula B into Y. And this is our base temperature. I'm denoting this by T naught, temperature of the base of fin at the base of fin. And the surrounding field have some temperature called TA. So TA is temperature of ambient and surrounding fluid. It can be air, water, anything. And K is thermal conductivity, which is constant everywhere. And H is our heat transfer coefficient, convective heat transfer coefficient. So now we have different parameters. Now we can derive this equation by calculating the heat which is going inside this element and the heat which is coming out of this element, and by equating heat and by balancing the energy on the element we can derive this equation. So I'm directly writing the general equation which comes out. So we all know about heat through conduction. Heat here will go through conduction, and it can be calculated by general formula. Now the heat which comes out can be written as, now we can generally balance the energy and we can derive the equation by using this energy balance. So we will talk about different cases here. Now different cases forms. First case is when fin is infinitely long. Second case is when the end of fin is insulated, and third case is when the fin is finite. That is, it is losing heat by convection. So we will discuss about all these cases. By heat balancing, we finally get a differential equation which can be written as, now here we can denote T minus TA as theta and HP by K as m square. So we can rewrite the equation as, now this is a second order differential equation and we have to find the general solution to this differential equation, and it can be written as, so this general equation can be used for deriving the above cases. First case is heat dissipation from an infinitely long fin. So suppose we have fin which is infinitely long. Suppose this is our fin, and here the length is till infinity. So this fin is infinitely long, and I have drawn the temperature profile. It is a graph between temperature and length of the fin, that is x. So from the graph you can observe that as the length is increasing, as we go to the farthest end of the fin, the temperature is decreasing, and at the final point, at the end point, it becomes equal to the ambient temperature. So here first of all we will write the boundary conditions. Now first boundary condition, you can observe that at x equal to 0, here temperature is equal to base temperature T naught. So here we write theta as T naught minus Ta. Second boundary condition is at x equal to infinity, that is when L tends to infinity. So here we have observed that temperature becomes equal to ambient temperature, that is here theta becomes 0. So by putting this value, when we put all these boundary condition in the equation which I have said before, we get a temperature distribution equation and a heat transfer equation. So I will write directly the equations. By using this boundary condition, we can derive that. So by putting the boundary condition in the above equation, we get a temperature distribution equation as, so we can rewrite it as, so the above equation represent the temperature distribution in an infinitely long film. Now we will find out heat transfer by conduction at the base. So we can find it easily by using the formula. And by putting the value, we get a final expression as, so these two are the required equations which we need to use for solving the problems. In second case, we will discuss about heat dissipation from fin which is insulated. Now look at this fin. This is our fin and this is our base temperature, that is T naught, and this is our starting point at x equal to 0, and length of fin is L. So here the fin tip is insulated. Now you can just observe the temperature profile. Here I have represented temperature. This is base temperature, and here it is, I'm showing ambient temperature, and theta is given as T minus Ta, and this is our temperature at L. So here we will write boundary conditions. Now first boundary condition is at x equal to 0, T is equal to T naught. So again theta will become T naught minus Ta. So we can also write it as theta naught because we are writing theta as T minus Ta. So theta naught will be represented as T naught minus Ta. And second boundary condition will be at x equal to L. Now since fin is insulated, so there will no heat transfer at the insulated tip. So Q will be 0. This means d theta by dx will be 0. So we can write equation. Now by solving this equation and by putting the boundary condition here, we can find out the temperature distribution equation and the heat transfer equation. So the final expression comes out to be, first of all, we will write temperature distribution equation. Now this is our temperature distribution equation. Now if you want to find temperature at a tip, that is theta L, then it can be written as This is our theta L. Now let us see what heat conduction equation is. So we can find this again by Fourier's equation by putting our value in Fourier's conduction of heat equation. So the final expression comes out to be, so this is our required equation. Now we know what theta naught is here. Theta naught is T naught minus TA. So we can directly put in a formula for solving problems. Now we have seen that for infinitely long fins, there is no tan hyperbolic ml, this quantity. So what happens when fin is infinitely long, then tan hyperbolic ml value equals to 1. So it is observed that when ml is greater than equal to 3, tan hyperbolic ml tends to 1. So this is the value for ml fin when it is assumed to be infinitely long. Now you have just seen in infinitely long fins that this one is missing. So it is missing because ml is greater than equal to 3 there. That's why the fin becomes infinitely long. So this formula can also be used for solving infinitely long fins by putting this value 1. Now we will discuss about third case, that is heat dissipation from a fin which is losing heat at the tip. Now just observe this fin. This is our base having temperature T naught and fin is having some finite length, that is L. So this is our length of fin, that is L. Now you can observe the temperature decreasing. Now at this point at x equal to L, the fin will lose heat and this heat will be equal to the heat by convection. So this is our heat by convection. This is area of surface which is losing heat. And first of all, we will write the boundary conditions. First boundary condition is at x equal to 0. We know that T is equal to T naught. That is theta is equal to theta naught. And second boundary equation is at x equal to L, Q conduction equals Q convection. Here you can observe this. So what we do, we directly equate the convection equation with conduction equation with convection equation. So we equate these both equations. After solving that, we get a temperature distribution equation and a heat transfer equation. Now we can write it as theta is equal to theta naught cos hyperbolic ml minus x plus h by mk sin hyperbolic ml minus x by cos hyperbolic ml plus h by mk sin hyperbolic ml. So this is our temperature distribution equation. And again we can use formula Q is equal to minus k d theta by dx at x equal to 0. By putting that above in this value, we get Q heat transfer rate as under root h p k a theta naught multiplied by tan hyperbolic ml plus h by mk by 1 plus h by mk tan hyperbolic ml. So this is our required equation. This is our required equation. Next topic is efficiency and effectiveness of fin. So we define efficiency of fin as ratio of actual heat transferred by fin to the maximum heat transferred by the fin if entire fin is at the base temperature. So we will write it as, First of all is actual heat transfer, which we find using the formula which we have discussed before. So that is actual heat transferred by the fin. Suppose it is written as Q fin and ratio to maximum heat transfer rate. Transfer rate if whole surface is maintained at the base temperature. Now again, three cases comes. Now for that three cases, we have to find out the efficiency of the fin. So if fin is infinitely long, then we can find efficiency by using formula. So this is our case one, which we have found the heat equation in case one, and this is our maximum heat transfer rate. Since we know that efficiency is Q actual by Q maximum, so this is our actual heat transfer and this is our maximum heat transfer. Similarly, we can find efficiency of fin which is insulated at tip to tan hyperbolic ml. So this equation we found in case 2, and this is our maximum heat transfer rate. Now if length is infinite, then again we can use actual heat transfer rate to maximum heat transfer rate ratio. This is tan hyperbolic ml h by mk plus h by mk dot tan hyperbolic ml. Now maximum heat transfer is written as PL plus B2 into theta naught. So this is our maximum heat transfer rate and this is our actual heat transfer rate. So using this formula, we can find the value of efficiency of fin. Now we will learn about fin effectiveness. Fin effectiveness is defined as the ratio of fin heat transfer rate to the heat transfer rate that would exist without fin. So we write it as heat transfer rate with fin to heat transfer rate without fin. So when I talk about infinitely long fin, then we can calculate it by putting the values in above equation. So this is the value when there is fin and this is the value when fin is absent. So by solving this we get, so this is the effectiveness when we talk about infinitely long fins. Similarly, we can find effectiveness for fin with insulated tip by only changing this Q with fin. So effectiveness can be found using all this. Now we have observed that insulation of a surface does not mean that it will reduce the heat transfer rate. Now we have learned in case of cylinders and spheres that sometimes it reduces the heat transfer rate, sometimes it increases the heat transfer rate. So here also when we talk about effectiveness, then it will not always increase the heat transfer rate. So it depends on the fin. So for before making any fins, we have to find the effectiveness of the fin. Thank you guys for watching this video, and if you want any improvement in this video, then you can comment me in the comment section, and if you found this video informative, then give a thumbs up.